proved last time. To remind you, if we have more than 4 v edges, we have the following. This is a v. We have that the crossing number of our graph is bounded below by some multiplicative constant, potentially, times e cubed over v squared. And this we did by averaging over all random subgraphs, induced subgraphs, and taking the expected value of both sides and applying the taking the expected value of both sides of the proposition that we had proved, the proof by oracle that we had from the graph theory section. So I want to apply this crossing number lemma to prove the following theorem, and this is Szemeredi-Trotter. And the name Trotter should be familiar because he's one of the co-authors of the book we use this semester. So Szemeredi-Trotter says, in any set of n points and m lines in the plane, number of incidences call that I, is bounded above by nm to the power 2/3 plus n plus m. So I'm going to prove that now, and I'm not going to give you their proof. Their proof is beautiful, but I want to give you a proof due to Senger, and it was in his crossing numbers and hard Erdős geometry problems or something like that. A paper in which he reproved this and the next result that I'll show you using his crossing number lemma. And this crossing number lemma really sits at the heart of a lot of these combinatorial problems in a meaningful way. So if you do have time, and it is a bit of an undertaking, after looking through this proof, if you did go back and read the original Szemeredi-Trotter paper, I feel like you can actually see the crossing number at work. Even though it's a different argument, you can kind of see what they argued with in place of crossings, and it's a very beautiful argument as well. But this kind of gets to the heart of it, I feel like, a little bit quicker. So let's prove this. So we're going to take our set of n points and m lines, and we're going to construct a graph. G with the n points as vertices and the I minus m segments between consecutive points on each line as edges. And my guess is that the n points is maybe not so mysterious, but the I minus m might be a little confusing. So where does the I minus m come from? Well, let's look at if I have a line and it has, say, 3 points on it, that line is going to contribute 3 incidences, an incidence being a pair PL where the point P is on the line L, like we discussed in class. But how many edges will we get in the graph? Well, we'd get one edge here because that's a consecutive segment between 2 points, one edge here because that's a consecutive segment between 2 points. And then these pieces of the line that go off to infinity, those do not form a proper edge in our graph. So how many edges do we get from each line? Well, precisely the number of incidences contributed by that line minus 1, because the edges occur between pairs of points. And think of this kind of like how when we were manufacturing chairs, how we were with the stars and bars problems, we were looking at the places to put dividers. So what we're doing is the edges are going to fall in between pairs of points, but there's always going to be sort of one less edge than the number of points on that line. So we count all of the incidences, and all of the incidences are the pairs of points and lines, and those incidences will agree with edges up to there's going to be one extra incidence for each line. So we keep that by taking the number of incidences and subtracting 1 every time we have a line. So we get I minus m. We're losing one edge per line. Okay. Now we have two cases. Okay. So case 1, this is that E is less than or equal to 4v. If E is less than or equal to 4v, what's that tell us? That tells us that I, the number of incidences, is bounded above by, E is I minus m, and that's bounded above by 4 times the number of vertices, which tells me I is less than or equal to m plus n. So I'm ignoring these multiplicative constants. And that takes care of the easy case, or the degenerate case. Now case 2, is going to be that E is bigger than 4v. And the case that E is bigger than 4v is, of course, where we're going to apply the crossing number lemma. So the crossing number lemma is going to give us a lower bound for the number of crossings. What's a good upper bound for the number of crossings? Well, we notice that the number of crossings, well, also known as CRG, has to be bounded above by the number of times that lines can cross. Because for two edges to cross, what does it mean for these two edges to cross? It means that those geometric lines had to be there in the first place. So the number of times that two lines can cross, well, again, we've got m lines, so the total number of times that a pair of lines could cross, well, generically, is as much as m choose 2. So this is bounded above by m choose 2, and m choose 2, I'm going to say, is roughly m squared. It's m times m minus 1 over 2, but we're ignoring multiplicative constants here. Now, because I've got this, I can comply the crossing number lemma. So I'm going to put CNL to denote that the crossing number of G is bounded below by E cubed over V squared. So the crossing number lemma gives us this fact. And we've just shown that the size of V squared. We've just shown that the crossing number of G is bounded above by m squared. So now let's put all of this information together. Well, you'll recall E is I minus m, quantity cubed. And if I multiply both sides of this, I'm going to cover up the crossing number. If I multiply both sides of this inequality by v squared, well, that's just n squared. So this is m squared times n squared. Here's my m squared, here's my n squared. And if I do the math here, I get that I is bounded above by mn to the 2/3 plus m. And if I combine this with this, I get exactly what I claimed. All right? So that is a proof of the Szemeredi-Trotter point line incidence theorem. I'm going to take a sip of tea. For anyone interested, this is about the nastiest possible abomination of tea that could exist. There you go, you saw it a little bit. This is decaf Earl Grey, which is already a crime. And then instead of putting a proper citrus into it, I put vanilla almond milk. I think this is like violating a Geneva Convention or something. Okay, so now let's get rid of this. Crossing number lemma, again, very useful stuff. We're now going to prove a theorem due to Spencer Szemeredi-Trotter. So two of the same authors, Szemeredi and Trotter, but now this time accompanied by Joel Spencer. This was the following year. I think Szemeredi-Trotter was 83, Spencer Szemeredi-Trotter is 84. So in any set of n points, in the plane, no distance can occur more than n to the 4/3 times. And this is, approximately, so no more than, squiggly, more than n to the 4/3 times. And I want to point out that this is related to Erdős's unit distance problem. He conjectured that the most often that any particular distance could occur in a set of n points in the plane would be something around linear, and so something around n to the 1. And so far, this is the best result we have. So this result was proved, like I said, in '84, or at least it was published in '84, and it's currently 2020, and this is still the best exponent in town. So there's a lot of work to do here, and mathematicians currently don't seem to know how to improve this bound. Okay, so let's prove this one though. So proof. We're going to follow a similar plan of attack to the previous one. And what we did there was we made a graph where we chose our points as vertices, and we chose the segments, the line segments connecting those points, as our edges. So in this, we're going to use that same kind of idea, but I'm going to go, there are some more technical issues, and I might sort of scrub out some of those technical obstructions. It's all written in detail in the notes, but as we're going, I might maybe talk through some pieces, but not write them down in complete detail because it gets a little fiddly. Okay, so proof. Again, we take our set of n points, we draw unit circles about each point. Now, when I say about, I mean centered at. And again, why am I drawing unit circles? Because if I get a bound on how often the distance 1 occurs, well, then I could dilate my set so that it counts any distance. So if it just so happens that the most popular distance in my set was 17, then I could scale the set down by 17 and 17 units, and then the unit distance would then count the distance 17 in the original set. So without loss of generality, we're going to assume that 1 is a most popular distance. Again, I'm saying a most popular because we don't know, there might be many most popular distances. So let's draw unit circles about each point, and then we're going to construct a graph. G, whose vertices are the n points, and whose edges are the arcs of circles between consecutive points. Okay, so what we're doing here is we're going to check the condition of the crossing number lemma again for this new graph, and apply our crossing number lemma in the case that this condition holds. In the case that this condition does not hold, we should have some easy argument that shows that we win. Okay, so case 1. This is the case that I'm jumping the gun here. So here's where we're going to have some details. So technically, I need to prune my graph, because I could have something like this. I draw a unit circle around this point, it looks like that. Draw a unit circle around this point, it looks like that. And now, if there's a point here and a point here, it just so happens that this pair of points has 2 edges. Okay, well, I don't want that to be a problem, because that does not satisfy my definition of graph, and this theorem was proved for graphs. Now, it turns out that there's an analogous proof that works for multigraphs, but we haven't gone through that proof. So what I'm going to do is I'm going to say, anytime that I have something like this, I'm just going to get rid of that. Okay, I'm going to get rid of one of these edges. All right. Moreover, I could have a circle here that has 1 point on it. Well, then in my graph, that would be a loop, right? That would be a vertex adjacent to itself. we're going to say we're going to get rid of that. Same thing if I have a circle with 2 points on it. This would be, again, multiple edges between pairs of points. So what I want to do is I want to say that this, I'll get rid of this edge, I'll get rid of this edge, and I'll get rid of this edge. And there's a careful argument that says that if I do this, I don't lose too many edges. And the way we're going to take care of this somewhat carefully is we're going to say, case 1, suppose that the number of edges is less than, so after pruning, after pulling everything off, suppose that the number of edges is less than or equal to 4 times the number of vertices. Well, then we have what? Well, the number of edges is equal to the number of times that I have a point circle incidence, which is not exactly equal to the number of unit distances. It will be twice the number of unit distances, because if I have a point on this circle, that means that this point was on the circle centered at that point, and so on for each of those points. But it's within a constant of the number of unit distances. So if I have fewer edges than 4 times the number of vertices, then I have that the number of unit distances, so using pound UD for the number of unit distances, is bounded above by, n, right? Because the number of edges is comparable to the number of unit distances. The number of vertices, this is 4 times the number of vertices, but we're ignoring multiplicative constants. So if the number of edges is small, then we have not many unit distances. We have no more than n, and my goal is to get no more than n to the 4/3. n being less than n to the 4/3, we're fine. Now, suppose, case 2, that E is bigger than 4v, again, after the pruning. Well, then I can apply the crossing number lemma. Again, with the crossing number lemma, that gives me a lower bound on the number of crossings, and now I want an upper bound on the number of crossings. Well, for sure, the maximum number of times that I can have crossings, that I can have edges crossing, is going to be related to the number of times that circles can cross. Distinct circles can cross at most twice, and there are n circles, so I have, well, that the number of crossings, I'll just write it all in one line here, is certainly no more than 2 crossings per circle, 2 crossings per pair of circles, times n choose 2 pairs of circles. This is, number of crossings per pair of circles, and this is the number of pairs of circles. Well, this is, again, n choose 2 is n times n minus 1 over 2, but I'm going to say that's roughly, ignoring constant multiples, that's roughly n squared. Since I've got the crossing number lemma, I've got this is bounded below by e cubed over v squared. Now, again, I take this over to the other side, and I say, well, the number of edges is comparable to the number of unit distances. So this tells me that the number of unit distances, I keep forgetting the letter U. I keep forgetting about U. The number of unit distances cubed, because that's the number of edges, is bounded above by, well, v is n, so I've got v squared is n squared. N squared times n squared is n to the 4th. And again, if I check the arithmetic, I get that the number of unit distances is bounded above by n to the 4/3. And this is the main argument. Now, what I've skipped over is that when we've removed edges, when we've pruned our graph, that we haven't removed too many edges. And again, like I said, the details for that are in the proof. In the proof in the notes. But loosely, what they say is, I'm going to remove some edges. Now, if I remove many edges, if I remove enough edges to change the order of magnitude of this, then this must have had a very small order of magnitude. And by order of magnitude, I mean compared to n. So if there were, n edges to begin with, then I'm removing n edges. Well, gosh, then I don't have an accurate reflection of my number of edges. But if I only had n edges, I don't need to do any of this, right? So that technical argument is laid out in more detail in the notes, but let me just say it's not difficult. It's more just bookkeeping. Thanks so much. Have a good evening.